guys, welcome to this grade 12 lesson. In today's lesson, we are going to be looking at trigonometry revision. So I know that for a lot of grade 12s, it is their favorite section, and I hope it's your favorite section too. It's one of my favorites, certainly. And it's one of those sections where you can actually get a lot of the marks in that section of the exam just by simply practicing and going over your past papers. Now, when we're talking about past papers, I'd like you guys to bear in mind something very important when you start going through your past papers, and that is to keep the mark allocation in mind. Now, you know that the marks on offer in an exam are obviously divided between the easy marks, the medium marks, and then you get your more difficult questions as well, okay? So while you are revising and going over your past papers, try to identify which are the easy marks, which are the medium marks, and which are for the more difficult marks, okay? So you identify which questions give you what marks. And, you know, even if you're practicing and it's just the easy marks and you think, oh, well, I can't get this, that's fine. It's just as long as you can identify where you need to spend a little bit more time. And then talking about time, remember the rule that I've already said to you guys. Keep in mind, it's a mark a minute. So what that means is, if a question is worth 5 marks, for example, the maximum amount of time you should spend on that question is 5 minutes. You can spend less than 5 minutes for sure, but don't go way over 5 minutes because you'll find yourself running out of time at the end of the exam. And you know, your question paper, you've got quite a lot of minutes to write it in, but it doesn't seem like a lot when you're in that panic mode and trying to rush through the exam to get to the end. So keep in mind that mark a minute, and keep in mind and look out for where are the easy marks when you are revising from your past papers, okay, as you should be doing by this time of the year. All right? Also, another important thing when we're dealing with trig especially is make sure you know how to use your calculator. Now, this is extremely important not only for trig but all throughout maths. Make sure that your calculator is also working before the exam. So if you've got batteries that need to be replace it before the exams rather than arriving on the day of the exam and realizing, ooh, my calculator battery life is not going to take me through those 3 hours. So make sure that your calculator is in working order, and also do not borrow a calculator. If for some reason your calculator packs up during an exam, do not borrow a calculator that you haven't worked on already, because you know that there's certain methods and steps and procedures you've got to follow when you enter the data into your calculator. So make sure that the calculator you are using in your exam is one that you've been using to practice on before the exam as well. All right. So this is common sense information, but sometimes we need to be reminded of it. The CAPS breakdown for the exam, while trigonometry accounts for about 43 marks in paper 2, and that's about 28% of the final exam. Okay, so that's quite a lot of marks for your final exam, and it is a section that you can do very well in by practicing through past papers, as I've said before. So talking about past papers, our first question for today comes from a past paper. This is from the DBE November 2015 paper 2, maths paper 2. This is question 5.1. Obviously, we're just dealing with trig in today's revision session, so this question is obviously on trig. I'd like you to take down this question and see how much or how far you can get in the next 3 minutes, which I'm going to give you to take down the question, and to also see how far you can get. You've got 1.1, 1.2, and 1.3 to do. So see how far you can get in the next 3 minutes and draw any necessary or relevant diagram in this time that I'm allocating to you. Okay, guys, so in this question, it's a very, very common question. You see it all the time when you go over past papers, which I hope that you've already started doing now. And it's one that involves a little bit of manipulation, you know, a little bit of working of your magic there to get it to a form that you can use, that's useful for you. So a trigonometric form that's useful for you, okay? So here you were given that sine of 23 degrees is equal to the square root of k. So really, you've just been given one bit of information if you just read that one line, okay? So everything that we're going to see in the rest of the question comes back to and has to come back to this very important piece of information that you've been given. Okay, if we carry on reading the question, it says, given that sine of 23 degrees is equal to the square root of k, determine in its simplest form the value of each of the following in terms of k, which means we need k's in the answer without using a calculator. All right. So the thing that we're going to use to help us here is obviously that key information, as I said, which is the sine of 23 degrees. But we're going to try and reduce each of the different ratios that they have given us in this question, try and reduce it or relate it back to sine 23. Why do we want to do that? Because that's the bit of information that we've been given, okay? So how do we go about the first one? Well, we've got sine of 203 degrees. So I start thinking, well, how is 203 related to 23? Okay, well, immediately, it's not immediately apparent, but if I said, and you can do this on the side, if you say 203 minus 23, what will you get? You'll get 180. So in other words, 203 degrees can be rewritten as 180 degrees plus 23. And that is very useful to me because now we've got it in a form where we can reduce 200 degrees. Okay, so sine of 200 degrees, we're going to rewrite that as sine of 180 degrees plus 23 degrees. Okay, you know from your reduction formulae and your reduction that you've been practicing so far that sine of 180 plus 23, we first look at where the angle is in relation to the ratio, and that means we need to consider the cast diagram. Okay, remember your cast diagram, it's a guide as to what angle is positive where. So all the trig ratios are positive in the first quadrant. Sine is positive in the second quadrant, tan is positive in the third quadrant, and cos is positive in the fourth quadrant. 180 plus, well, we know that in the first quadrant all the angles are acute, meaning that they are less than 90 degrees. And so if I'm looking for an angle 180 plus 23, that's going to fall into the third quadrant, and only tan is positive there. So therefore, sine of 180 plus 23 degrees will be negative sine 23. And we know that sine of 23 had a value of square root k. Okay, so the first one should have been relatively simple for most of you. Okay, let's move on to 1.2. So here you've got cos of 23. And this is the one where a lot of learners tend to get a little bit stuck. And they say, but this 23 now, how am I going to make it sine of 23 when it's already got another trig function, in this case cos? And guys, you should have come across this a lot by now because you should be practicing. As I keep saying, throughout this lesson, I'm going to remind you, and in all our revision lessons, you need to already start practicing by this time of the year. Cos of 23 degrees, we cannot relate it directly to sine 23, okay? So what we do to help us to work out the value for cos of 23 is we introduce what we call a Pythagoras triangle. And that looks like this, and this, as I said, should be familiar to most of you. So I know that sine of 23 degrees is equal to the square root of k. I also know that 23 degrees falls in the first quadrant. So I can draw a triangle, a Pythagoras triangle, meaning that the one side, the vertical side, is perpendicular to the x-axis. I just want to make that a little bit squarer. Okay, so that's perpendicular to the x-axis. And our angle 23 degrees is going to sit here inside the triangle. All right, sine of 23, from definition, we also know that sine of any angle is opposite over hypotenuse. I also should realize that the square root of k can be written as square root k over 1. Okay, so therefore, relating sine 23 to the definition of sine, I can say that sine of 23 degrees is going to be opposite over my hypotenuse. So I can draw the triangle from that given information. And in that way, I get an angle of 23 degrees, which I can use to help me find cos of 23. The reason I drew that 90-degree, remember, this is a Pythagoras triangle. In other words, we've got a hypotenuse, we've got a right angle. I can use my hypotenuse, which is 1, my opposite side of my vertical length, which is the square root of k. I can use that to help me find the length of x for this triangle. So I can set it up as follows. By Pythagoras, we know that x squared plus y squared is equal to r squared. X is what we are looking for, so therefore it's going to be the difference, r squared minus y squared. R had a value of 1, and y had a value of the square root of k. Okay, so therefore, you'll get 1 minus, if you square the square root, you're just going to end up with k, because if you squaring a square root, you're basically saying square root of k times square root of k, which is equal to the square root of k squared, which will just give you k. So obviously the square root and the square cancelling out there. Okay, so x squared is equal to 1 minus k, therefore x will be the square root of 1 minus k. Plus or minus, because we are in the first quadrant, we're only interested in the positive answer. So therefore x is the square root of 1 minus k. Okay, so hopefully you'll see the usefulness in that now. From my definition, I know that cos is adjacent over hypotenuse. Adjacent to the angle 23 degrees is the square root of 1 minus k. And your hypotenuse is 1. So we can just leave that as cos 23 is equal to the square root of 1 minus k. Okay, let's have a look at the next one. And here again, we are asked for an angle that relates to what we were given. We were given sine of 23. Here we asked for tan of negative 23. So this triangle could be useful, or we could also use an identity, because remember tan is equal to, tan of theta is equal to sine theta over cos theta. So we could use that. All right, it's up to you which you prefer to use. Ultimately, you should get the same answer. The interesting thing that you've been given here is that you've got tan of a negative angle. Now remember, all your negative acute angles, meaning less than 90 degrees, those all end up in the fourth quadrant. So negative 23 degrees is a measurement in the fourth quadrant, okay? So therefore, we know that tan of negative 23 will be negative tan 23. So that tells me the overall ratio, the sign of the ratio is going to be negative. It's an important concept. Make sure you understand that. Tan of negative 23, because tan of negative 23 lies in the fourth quadrant, and we know that tan is negative there. In fact, the only ratio of a negative angle that would be positive in the fourth quadrant is cos, okay? So tan of negative 23 will give me negative tan 23. The overall sign is going to be negative, all right? You can also obviously double check on your calculator, but in this question we was told not to use the calculator. I said to you there's two ways you can do this. You can go back to your Pythagoras diagram and read off tan there, or we can remember that tan of 23 is sine 23 over cos 23. And we were given that sine 23 was the square root of k. We just worked out that cos of 23 was square root of 1 minus k. In its simplest form, because these are both square roots, we can write this underneath 1 square root as follows. So this would be the square root of k over 1 minus k. Okay, guys. All right, I think that's quite a lot of information to take in right now. So let's take a quick break before we continue our discussion and our questions from past papers regarding trig. Back after this. Welcome back, everyone, to our lesson on trigonometric revision. Okay, so here, grade 12s, we are looking at questions from past papers. If you've got the past paper with you, then please refer to the questions in your past paper, or you can find them online, or obviously you can take down the question and the important information, because I do give you time to do that, as I'm going to do right now. In this next question, it comes from the DBE 2015 paper 2. This is question 5.3. I'll give you a couple of minutes to take this one down. You've got 2 minutes. Okay, so this question should seem very familiar to all of you. It's a general solution question. So remember, if we think about this in a picture form, and trig is one of those nice subjects where you can relate it back to pictures. So I'm really looking for, when I'm talking about general solutions, I'm looking for the different points on the graph that has the same output value. Output, remember, your dependent value, your function value, your y value, all those terms mean the same thing. So I'm looking for different x values that give me the same function value. That's essentially what you are doing when you're solving a general solution. So this is what I'm saying, and I'm going to draw it for you because I mentioned that it is quite a good idea to draw a graph. So before we actually get into the question, say we end up with, when we simplify this, say we end up with a cos function, okay? So let's just move this across so it's more equal. So say you have a cos graph, it's going to look like that, and obviously it continues infinitely in both directions, okay? So this is from 0 to 360 on the right hand side, and then from 0 to negative 360 on the left hand side. Now obviously this graph can continue infinitely in both directions, but what you'll find is there's points on the graph that have the same function value. So for example, where I'm putting that white dot, in fact, let's make it clearer in this way. If I take this blue line and run it through the y-axis, that gives me the same function value for the graph. So in other words, wherever the graph hits the cos graph, those values are going to have the same y value, but there are different x values for which that can happen. Do you see that? So if I look just at that simple graph that I've put in there, there's already 4 solutions between minus 360 and 360, 4 different solutions for x. You can imagine that if we were to take 360 and multiply by n, which will give you an infinite number of multiples, you can have many more solutions, and hence it's called a general solution for a trig equation. Okay. Now, often the most tricky part in solving a general solution is getting through the first part of the question, and I'm just going to change my pen there. So we've got cos of 2x minus 7 cos x minus 3 is equal to 0. So the trickiest part is deciding, well, what's the next step? So the next step is generally always going to be, well, find an expansion if you can, or factorize if you can. In this case, we know that cos of 2x does have an expanded form. We can rewrite that as 2 cos squared x minus 1. And I will leave the minus 7 cos x and the minus 3 as they are. Okay? I can simplify a little bit further. So I get 2 cos squared x minus 7 cos x minus 4. And what you guys should have noticed there is I've rewritten this in descending powers of cos of x. Okay, so here I've got cos squared x to start with, then we go cos x, and then there's obviously a constant term. You want to get it in this form when you are dealing with a trinomial. So this reminds us of a quadratic trinomial, which you all should be very familiar with by now, okay? But we're just obviously using trig ratios, so yes, it can be confusing. So what I suggest to learners who are struggling to see the factorized form of this trigonometric trinomial is to use a k. So what you can say, and that sounded a bit use a k, use the letter k to help you simplify this. So you can say let cos of x equal k, and that will help you simplify this trinomial a little bit more. So I will get 2k squared, see what I've done? Where there's a cos x, I've put in a k, minus 7k minus 4 is equal to 0. If you can see the trinomial straight away, please, you don't need to do this step. This is only if you're battling with the trinomial. Okay, we can factorize that into 2k times k, 4 and 1, minus 4 in the one bracket plus 1 in the other. Okay, so that's your factorized form. We now can replace k with what it represented, which was cos. So we will end up with 2 cos x plus 1 times cos x minus 4. Hopefully you are all following and you understand that all I've done there is I've replaced the k with the cos x that we said it must be equal to. This is now the factorized form of that trinomial. Okay, guys, so this in between is an optional step. You can go straight from there all the way to the final factorization. Okay, now we've got factor times factor equal to 0. We can apply the zero factor rule, which says if you've got a factor times a factor equal to 0, you let each factor equal 0 and solve for your variable. Okay, so let's concentrate on the second solution first, which is if we take the minus 4 over to the right hand side, we'd get cos x is equal to 4. Now that we know has no solution. Why does it have no solution? Well, if we go back to the cos graph that I've drawn up here, you know that the maximum point, or you should know that the maximum point of a cos graph is 1 and the minimum point is minus 1. The value of 4 is sitting somewhere there. Does the cos graph ever reach that blue line? No. So therefore there is no solution for x there. Okay? Let's go back to that side. We've got 2 cos x plus 1 equal to 0. I'm going to take the plus 1 over to the right-hand side, so it becomes minus 1. So just as you would in any linear equation. Divide both sides by 2, so you get cos x is equal to negative a half. Now at this point there are different methods to write out the general solution. The method I'm going to use is I'm going to say that if I've got cos of x equal to an angle, then my answer, my general solution is going to be plus or minus that reference angle plus k times 360. There are different methods to get to your general solution. As long as you get the same solutions out of substituting values for k, you are on the right track. So the other method you could do this, if you're getting a bit confused with what I'm talking about, you can then say, well, where is cos of x negative? Put that in the right quadrant. So you'll get a reference angle and you won't put this negative into the calculator. So you'll just go on your calculator, shift cos a half, you get a reference angle, and then you put it into the right quadrant to get your general solutions. I'm not going to do it that way. The way I'm going to do it, which should really be a way most of you should start learning this at school. It is the more improved version of working out a general solution. I'm going to say shift cos off, and I put in the negative a half. Okay, and you get 120 degrees. Therefore, x is going to be equal to plus or minus 120 degrees plus k times 360. That's the general solution. Okay, you can use a k or an n. It really doesn't matter as long as you state that whatever variable you've used is an element of integers. Okay, hopefully all of you got to that point, or you at least understand better how to get to that point. Okay, I want to quickly go into our next question to give you some time to just take this down. Again, if you've got a past paper, you should be working through it. Hopefully this is one of the past papers that you have with you. This now comes from the same paper, the November 2015 paper. This is question 5.4. I'm only going to give you guys, it's a very quick question. I'm only going to give, well, to take down anyway. I'm only going to give you just a minute just to take it down. Okay, guys, so this question, while it was very quick to take down, it's not that quick to actually do. So I want to give you a chance to try and complete this question, see how far you can get during this break. We'll be back after this. Welcome back. Before the break, I gave you a question to take down. You were given that sine of theta is equal to 1 over 3, and then you were asked to calculate the numerical value of sine of 3 theta without using a calculator. This was for 5 marks, and it does come from the November 2015 paper. I hope that you've had enough time to start expanding the sine of 3 theta and getting somewhere, okay? Let's have a look at this expansion. So I'm given that sine of theta is equal to 1/3. I'm not going to start there. You might think, okay, well, maybe I should draw a diagram. It's not going to be a good idea for this question, and specifically because you've got a compound angle. So sine of 3 theta, we're going to rewrite, because 3 theta we can break up into 2 theta plus theta. Because what is 2 plus 1? 3. There we go. So that's how we decided that that's what we're going to use, okay? Now the compound expansion for sine of a plus b, so sine of a plus b, going back to our definition for sine of a compound angle, that would be, the expansion is sine a cos b. Your sign in the middle stays the same as the sign inside the bracket, plus cos a times sine b. Okay, so using that, applying it to the new compound angles, which is 2 theta and theta, I'm going to get the following. Sine 2 theta times cos theta plus cos 2 theta times sine theta. Okay, the expansion here is a little bit long. It's not that tricky, but it is quite long, so it's easy to make mistakes. Sine of 2 theta, the double angle expansion is going to be 2 sine theta times cos theta, so I rewrite that. This cos theta times the cos theta that's already there, I'm doing it in one step, is going to become cos squared theta. Cos of 2 theta, remember you're dealing with a double angle expansion. There's 3 different options. But we want to try and work towards sine because that's the value we've been given. So what I'm going to do is I'm going to choose cos of 2 theta is equal to 1 minus 2 sine squared theta as my expanded form, times by sine theta. Okay? Okay, so it's quite a process. Let's go to the next step. We're going to say cos squared theta we can rewrite as 1 minus sine squared, because remember your basic identity, sine squared plus cos squared is 1. All right, plus let's multiply sine theta into this bracket, so I get plus sine theta minus 2 sine cubed theta. Let's then multiply the ratio outside the bracket into the bracket in the first term. So we get 2 sine theta times 1, which is just 2 sine theta. 2 sine theta times negative sine squared theta is going to give me negative 2 sine cubed theta. And here we're looking pretty good because everything is already in terms of sine. Okay, so I can now add like terms. 2 sine theta plus sine theta is 3 sine theta minus 2 sine cubed theta minus 2 sine cubed theta is minus 4 sine cubed theta. Okay, so at this point we're really happy because now that everything's in terms of sine theta and you know that the value for that trig ratio is 1/3, we're simply going to substitute, okay? So we're just doing a bit of algebra now to tidy this up. In place of sine theta, I put in 1/3 because that was what I was given, minus sine cubed theta, which is 1/3 cubed. And I get, we might need to go to a calculator just now, 3 times 1/3, I'm going to get 1 minus 4 over minus 4 times 1 over 27. All right. So I get 1 minus 4 over 27. You can use a calculator if you want to, or you can rewrite 1 as 27 over 27, and therefore I will get 27 minus 4 is 23 in the numerator over 27. Okay, so you saw that after all of that long expansion for sine 3 theta, we get to a nice answer. Some of you might say, well, it's not such a nice answer because it's a fraction, but hey, it's still a nice answer. It's still a compact answer. Using that very long expansion, we get to a compact answer for this ratio. Okay, guys, the next question is a very nice, interesting question, as these all are. This one is about trig graphs, and I want to give you a chance really to have a look at the diagrams. Take down the diagram if you have enough time. Take down the diagram so that you can answer the questions with me as we go through it. I'm just going to give you guys 2 minutes to have a look at this. Okay, everyone, so hopefully it was enough time for you to take the question down, but we're going to read through it, so relax. If you didn't get it all down, don't worry, let's go through it. Okay, so you are told that in the diagram below, the graph of f of x is equal to cos x plus q. So let's identify f. So on my, my axis, I see that. That is the graph of f, and that's the graph. F is equal to cos x plus q. So already you should start thinking about what's happened to this graph. I see a plus q, so that means to me, in my mind, I start thinking there is a vertical shift, which there has been, of course. And then we see that g of x is equal to sine of x plus c. So g of x, let's use a different color, in fact. G of x is equal to sine of x plus p. So that you should already start thinking tells you that there's a horizontal movement that has occurred in the normal sine graph. So these two graphs are sketched on the same system of axes on the domain minus 240 degrees to 240 degrees. The graphs intersect at 0.5. All right, so that's obviously on your y-axis. That's that point there. They also intersect at minus 120 degrees and minus 1. So that's that point. And 240 degrees and minus 1. So basically, they've given you all the points of intersection. The first question says, determine the values of P and Q. All right, so you've got two unknown values. You've got P and Q, which means that you need to find those values. In other words, find the equations of the graph. The one way you can approach this is to do it by inspection. So you really know quite well what the sine graph, the original sine x graph with no vertical or horizontal shifts, you know what that looks like, or you can draw it on your grid and you can compare it and then just by inspection work out what the value of P is. In a similar way, you would draw your normal cos graph without any vertical or horizontal changes and then work out what the value of Q is. Now, I prefer to do it in an algebraic way because it takes away any stress that you may have made a mistake when you drew your original graph, or maybe you didn't quite understand whether the shift in P was to the left or to the right or what was going on. So let's do it algebraically. You know, like just with any function, if they've given you a point that lies on the graph, if you substitute the value for x into your input value, what should you get? You should get the y value out, right? So therefore, to find the value of P, I would like to suggest to you guys that the best way to do this, to find the value of P, is to substitute a point that's been given to you on the graph. So I know that 0 degrees and a half is a point of intersection of both the sine and cos graphs. So for 4.1, we are going to look at g of x, which is equal to sine of x plus p. And we're going to find the value of p by simply substituting a point that we were given. And as I said, let's use 0 degrees and a half. So in other words, when my x value is 0, the y value that I get out is what? It's a half. Okay. So therefore, this is what I get. I get a simple now trig equation where I have sine of 0 degrees plus p is simply sine of p, which is equal to a half. You can do a quick calculation on your calculator or look at your special angle diagrams and you'll see that p is equal to 30 degrees. Okay, you don't even have to worry about what your signs or your values are. It's already correct. Okay, so you don't have to now think about, has this graph moved to the right? Has it moved to the left? Although you should be investigating your graphs in that way, using this algebraic method, you get the answer straight away. Okay, so it is a quicker way to work out the value of P. So therefore, P is equal to 30 degrees. Let's have a look now at Q. So remember, that's the graph f of x is equal to cos x plus q. You can again use the same point. You can use the 0 and a half, and in fact I'm going to do that. You could, although, you could try and use minus 120 degrees and minus 1. If you wanted to, you could use that point as well, or the point 240 degrees and minus 1. I'm going to use 0 and a half, it's more convenient. So in place of x, I'm substituting 0. And that means that my output value should be a half. My function value is a half. And I'm simply going to solve for q. Cos of 0 degrees is 1. 1 plus q is equal to a half. So therefore, taking the 1 over to the right-hand side, you get that q is 1 minus a half, which is negative a half. All right. So those are quick algebraic methods to help you in finding the equation of a graph when you've been given points that lie on the graph. Okay. All right. Let's have a look at the next question. Here you're asked to determine the values of x in the interval minus 240 to 240 degrees for which the graph of f is greater than g of x. So really what you're looking for here is where this cos graph is going to lie above the sine graph. Where's the graph of f greater than the graph of g? So if we had to put this into algebraic terms, we're looking for where the y values of the one graph are bigger than the y values of the other graph. So we look through the graphs and we see that, okay, remember f being your cos graph, we're looking at, and I'm going to just highlight it in a little bit better for you guys to see. So this is the graph here. We're looking for where that graph lies above the sine graph. And I can see that this happens at only one interval. It happens between minus 120 degrees and 0 degrees. In that section, you can see that all the values for your cos graph, every single one of them, any y value lies above the y values of the other graph. So therefore, it's in the interval. Remember, this is an interval. It's not a specific point. It's over an entire interval that this happens. So it's in the interval, x is an element from, and they just said greater than, so you're going to use an open bracket. So it's from minus 120 degrees to 0 degrees. All right, and I quickly want to have a look at the last question, which says, describe a transformation that the graph of G, so your sine graph has to undergo to form the graph of H, where H of x is equal to negative cos x. Okay, so let's just erase this quickly and have a look at what we're saying. So we're looking at the graph of G. We want that graph. What transformation must it undergo to become a negative cos x graph? Well, it's going to look, if I just superimpose now my negative cos x graph, it's going to look something like that, okay? And just going to roughly put it in there. Obviously, the value's going off. And if I look at now the sine graph, which let's just highlight for you guys in a purple so that it's easier for you to tell which graphs I'm looking at. You've got to look at those two and see, well, how can you move the sine graph or transform the sine graph to get the negative cos graph? For me, the most obvious point to look at is the y-intercept. So I can see that my normal cos graph, my negative cos x graph, sorry, not my normal graph, so h of x is equal to negative cos x. I see that that has a minimum value of minus 1 at 0 degrees. Now, in order for this sine graph to transform and look the same, you will see that it needs to move, right? It needs to move. So it needs to move, look at that, it needs to move to that position there. And that movement, what is that movement? It's 120 degrees. Okay, let me undo that so you can see what's at that point. That's at 120 degrees, negative 120 degrees. If I move this sine graph, sine of x plus 30 degrees, if I move it 120 degrees to the right, I end up with the negative cos x graph. And certainly other transformations could give you the same answer, but the one answer here is move the graph 120 degrees to the right. There is more than one way, however, guys, to get to that same answer. All right. I'm going to leave it there because I am running out of time. I hope that you've all enjoyed the lesson and that you've learned a lot and this has inspired you to start studying and revising early. Until next time, goodbye.